Tonight, we're going to talk about something that has no mass, no size, and no experience of time, and yet carries the energy that makes stars shine, the force that holds atoms together, and every image your eyes have ever formed. A photon. Light touches nearly every part of your life without you ever thinking about what it's made of. It wakes you up in the morning. It lets you see this screen right now, and it carries images of galaxies across billions of light years directly into your eyes. But you've never seen one directly. You've only ever seen what they do when they hit something. And yet the question of what one actually is took 3 centuries, several revolutions in physics, and still doesn't have a fully comfortable answer. It can behave like a particle in one experiment and like a wave in another, and it cannot, under any circumstances, ever slow down. By the end of tonight, you're going to understand what a photon really is, why it can never stand still, and why the question of what it's made of opens a door into the most unsettling territory in all of science. Before we begin, if you enjoy these topics as much as we do, make sure to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with something simple. Turn on a lamp. What's actually happening when light fills the room? Most people would say photons are being produced and bouncing off surfaces. That's correct, as far as it goes. But it doesn't tell you what a photon is. For most of human history, no one knew. And the debate over what light is, at the deepest level, was not resolved quietly. It was a genuine intellectual conflict spanning 3 centuries, involving some of the sharpest minds in the history of science, and producing answers so strange that even the people who found them weren't entirely comfortable with what they'd discovered. Isaac Newton believed light was made of particles, tiny corpuscles, he called them, fired outward from a source and traveling in straight lines. This explained why light cast sharp shadows. If light were a wave, it should bend around corners the way sound does. You can hear someone talking around the edge of a building, even when you can't see them, because sound waves diffract around edges. Newton argued that if light were a wave, it should do the same. But light doesn't bend around corners, at least not noticeably under everyday conditions. It casts sharp-edged shadows. So Newton concluded it must be particles. His theory also explained reflection. Light bouncing off a mirror follows the same angle of incidence equals angle of reflection rule that a ball bouncing off a wall would follow. And it explained refraction, the bending of light as it passes from air into water or glass. Different color particles of light would interact differently with the medium, Newton argued, and bend by different amounts, which is why a prism separates white light into its spectrum of colors. Newton's particle theory of light was the dominant view for over a century, largely because Newton himself was the dominant figure in natural philosophy. His Principia Mathematica had transformed physics. His laws of motion and universal gravitation explained the movements of planets, the behavior of projectiles, the rise and fall of tides. He had essentially invented what we now call classical mechanics. If Newton said light was made of particles, you needed extraordinary evidence to disagree. Then, in the early 1800s, Thomas Young disagreed. Young was a physician by training, a polymath who had contributed to the decipherment of Egyptian hieroglyphics, the theory of elasticity in materials, and the physiology of color vision. He was also interested in the nature of light, and in 1801, he set up what became one of the most famous experiments in the history of science. Young took a light source and shone it through a barrier with 2 narrow slits cut into it. Behind the barrier, he placed a screen. If light were made of particles, like Newton believed, you'd expect to see two bright bands on the screen, one behind each slit, with a dark area in between them. That's not what appeared. Instead, the screen showed a pattern of alternating bright and dark stripes, spreading across its entire width, an interference pattern. The same kind of pattern you see when two sets of ripples on a pond cross each other. When two sets of water waves overlap, something specific happens at every point where they meet. Where two crests arrive at the same place at the same time, they add together. The water rises higher than either crest alone. Where a crest meets a trough, they cancel out and the water stays flat. And where two troughs meet, they add to produce a deeper trough. This process of addition and cancellation is called interference. It's the signature of waves. Young's experiment showed that light was doing the same thing. Waves emerging from both slits simultaneously, overlapping in space, reinforcing each other in some places and cancelling each other in others. The bright bands formed where the light from the two slits arrived in phase. Their crests aligned. The dark bands formed where light from the two slits arrived out of phase, their crests and troughs cancelling. Particles don't do that. Particles fired through two slits either go through one slit or the other. They pile up in two bands behind the two slits. They don't spread out across the screen in alternating stripes. Young published his results, and they were initially dismissed. The authority of Newton was too great, but the evidence was undeniable, and over the following decades, other physicists confirmed and extended Young's results. The wave theory of light gained support. Then, Augustin-Jean Fresnel, a French physicist working in the 1810s and 1820s, provided a mathematical framework that explained not just interference, but the detailed patterns of diffraction around edges and through openings. His calculations predicted the precise positions of the bright and dark fringes in interference patterns. They agreed with experiment precisely. There's a famous anecdote about this. When Fresnel submitted his wave theory of light to the French Academy of Sciences in 1819, the review committee included Siméon Denis Poisson, who was skeptical. Poisson applied Fresnel's mathematics to a specific case, a circular disk placed in a beam of light. Fresnel's equations predicted that there should be a bright spot of light at the very center of the shadow cast by the disk. Poisson thought this prediction was absurd and intended it as a reductio ad absurdum, a bright spot at the center of a shadow. Obviously, nonsense. The committee actually went and looked. The bright spot was there, exactly where Fresnel's equations said it would be. Poisson had accidentally provided one of the most striking experimental confirmations of the wave theory of light. The spot is now called the Poisson spot, or sometimes the Arago spot, after Dominique Arago, who oversaw the experiment. Newton was wrong, or so it seemed at the time. By the mid-1800s, James Clerk Maxwell had built something even more powerful. Over a series of papers published between 1861 and 1865, he assembled everything known about electric fields, magnetic fields, electric currents, and magnetic forces into a compact set of 4 elegant equations. These are now called Maxwell's equations. They describe how electric charges create electric fields, how electric currents create magnetic fields, how changing magnetic fields create electric fields, and how changing electric fields create magnetic fields. That last relationship, changing electric fields creating magnetic fields, was Maxwell's crucial addition to what was already known. It was not directly observed in any experiment at the time. Maxwell added it based on theoretical arguments about consistency. Without it, his equations were internally contradictory in certain situations. He called the additional term the displacement current. And when he put all four equations together, he found that they predicted something remarkable. An oscillating electric field would create an oscillating magnetic field, which would create an oscillating electric field, and so on, sustaining each other indefinitely in a propagating wave. He calculated the speed at which this wave would travel through space. To do this, he needed two quantities that had been measured in purely electrical experiments. One was the permittivity of free space, which describes how easily electric fields form. The other was the permeability of free space, which describes how easily magnetic fields form. Neither had anything to do with light. Both had been measured in laboratories. Maxwell combined them. The speed came out to the same number as the measured speed of light. Not approximately, exactly. Within the precision of the measurements available to Maxwell, it was identical. The implication was unavoidable. Light was an electromagnetic wave, an oscillating pattern of coupled electric and magnetic fields, each sustaining the other, spreading outward from its source at 300,000 kilometers per second. This unified three previously separate domains of physics: electricity, magnetism, and optics. They were all aspects of the same underlying phenomenon. Maxwell's achievement was one of the greatest in the history of science. The physics community celebrated. The wave theory of light was confirmed by both experiment and theory. Confirmed comprehensively. Case closed. Then the late 1800s arrived, and something strange started happening in laboratories. Physicists were shining ultraviolet light onto metal surfaces and watching electrons get knocked loose. This effect, the photoelectric effect, had been noticed first by Heinrich Hertz in 1887 while he was doing experiments on radio waves. He noticed that electrical sparks between metal electrodes jumped more easily when the electrodes were illuminated by ultraviolet light. He didn't know why. He published the observation and moved on to other things. Subsequent experiments by Wilhelm Holwachs and Philipp Lenard explored this effect in more detail. They found they could measure the energy of the electrons that were knocked loose, and what they found was disturbing. If you used ultraviolet light of a certain frequency and measured the maximum energy of the electrons that were knocked loose, you got a specific value. When you increased the brightness of that ultraviolet light, more electrons were knocked loose, but the maximum energy of each individual electron remained the same as before. If you then switched to a different color of light, say red light, and shone it at the same metal surface, no electrons came loose at all. Not one. No matter how bright the red light was. No matter how long you left it on. This made no sense under the wave theory. Waves carry energy continuously across a surface. A brighter wave deposits more energy per unit time, per unit area. A dim violet light shouldn't knock out electrons, while a blazing red spotlight fails to dislodge a single one. The energy in the wave should be the determining factor. And the brightness should determine whether electrons are released, not the color. But that's the opposite of what the experiments showed. The color, the frequency of the light, determined whether electrons were released at all. The brightness only controlled how many were released per second. The wave theory of light couldn't explain this. Lenard received the Nobel Prize in Physics in 1905, partly for this work. The same year, Einstein explained it. In 1900, a German physicist named Max Planck had been working on a completely separate problem. He was trying to explain the spectrum of radiation emitted by hot objects. When you heat a material until it glows, it emits a specific distribution of light frequencies called blackbody radiation. The shape of this distribution depends only on the temperature of the object, not on what the object is made of. A heated piece of steel, a heated piece of carbon, a heated piece of ceramic, all at the same temperature, emit exactly the same spectrum. This had been confirmed in laboratories to high precision. Every existing theoretical model failed to reproduce it. The model, based on counting the number of electromagnetic wave modes available at each frequency, predicted infinite energy at high frequencies, which is obviously wrong. This failure was called the ultraviolet catastrophe. Planck spent months grinding through the mathematics, trying every approach. He eventually found an equation that fit the experimental data perfectly across all frequencies. But to make it work, he had to assume that energy was emitted in discrete chunks proportional to the frequency, not continuously, as a wave would. In chunks, each with an energy equal to a constant, h, multiplied by the frequency, f. He called these chunks quanta. The value of his constant, h, which we now call Planck's constant, is 6.626 times 10 to the minus 34 joule seconds. It's an extraordinarily small number. At everyday scales, it's essentially zero, which is why you don't notice the discreteness of electromagnetic energy when you turn on a light. The quanta are so small that the continuous wave approximation is almost perfect for any macroscopic situation. But at the scale of individual electrons in a metal surface, the discreteness matters enormously. Planck wasn't happy about the quantization. He thought it was a mathematical trick to make the equation work, not a statement about physical reality. He assumed a classical explanation would eventually emerge that made the discrete packets unnecessary. He spent years after 1900 trying to derive the same result without quantization. He couldn't do it. In 1905, Albert Einstein published one of the most productive years of scientific work in history. In that single year, he explained Brownian motion, developed special relativity, and proposed the quantum theory of light. Einstein read Planck's work and took it completely seriously. Where Planck had quantized the emission of light reluctantly, Einstein proposed that light itself existed in discrete packets, individual units of electromagnetic energy traveling through space. He used this idea to explain the photoelectric effect immediately and precisely. The reason low-frequency red light couldn't knock electrons loose, regardless of brightness, was this. Each individual packet of red light carried a specific amount of energy determined by the formula E equals h times f. At red light frequencies, each packet carried less energy than the minimum needed to free an electron from the metal. You could pile on as many red light packets as you wanted by increasing the brightness. But if each packet carried less than the threshold energy, none of them would work. More packets just meant more failed attempts. Violet and ultraviolet light packets carried more energy because of their higher frequency. More than enough to free an electron. So a dim ultraviolet source would successfully knock out electrons, while a powerful red light source would not. And the energy of each freed electron would equal the energy of one photon minus the minimum energy needed to escape the metal. This is exactly what Lenard's measurements showed. Einstein had cracked it. The amount of energy in each packet was proportional to the frequency of the light. Einstein called these packets light quanta. His formula said energy equals Planck's constant times frequency. This was more than just a solution to the photoelectric effect. Einstein was saying that light, which every experiment for the previous century had confirmed was a wave, was also a particle. Newton had been right. And Young had also been right. Both at the same time. Simultaneously. This was not a comfortable place for physics to be. The wave theory had been confirmed by too many experiments to abandon. But the particle-like behavior in the photoelectric effect was also too clear to ignore. When Einstein was nominated for the Nobel Prize years later, the Nobel Committee was still uneasy about the quantum interpretation of light. They awarded the prize in 1921, with the photoelectric effect listed explicitly as the reason in the citation. Not special relativity, not general relativity, the photon. It's worth noting that Planck had already received the Nobel Prize in 1918 for his discovery of energy quanta. 2 Nobel Prizes, 3 years apart, built from the same crack in classical physics. The word photon itself came a few years later. In 1926, the American chemist Gilbert Lewis coined the term in a letter to Nature. He used it to describe what he thought was a carrier of radiant energy in a slightly different theoretical context. His theory was wrong, but the name stuck. By the 1930s, the physics community had adopted the word photon to mean what Einstein had called a light quantum, a single discrete packet of electromagnetic energy. Further confirmation came from Arthur Compton in 1923. Compton shone X-rays at electrons and measured what happened. If X-rays were purely waves, they should scatter off electrons elastically, changing direction but not frequency. But that's not what Compton found. The scattered X-rays had a longer wavelength than the incident X-rays. They had lost energy. The amount of energy lost depended precisely on the angle at which the X-ray bounced off. This matched perfectly with the calculation of what would happen if you treated the X-ray as a particle with a specific momentum and computed the collision mechanics exactly as you would for 2 billiard balls. The scattered X-ray came off at a different angle and with reduced energy because it had transferred some momentum to the electron. The electron recoiled like a struck billiard ball. Particle behavior. Unmistakable. Compton received the Nobel Prize for this in 1927. By the late 1920s, the particle nature of light was established beyond serious dispute. The question was no longer whether a photon could behave as a particle. The question was how the same thing could be both a particle and a wave. That question has still not been fully resolved to everyone's satisfaction. But it had a deeper consequence. Louis de Broglie, a French physicist, extended the logic of wave-particle duality in the opposite direction. If light, which was known as a wave, could behave as a particle, perhaps electrons and protons, which were known as particles, could behave as waves. In his doctoral thesis in 1924, de Broglie proposed that all matter has an associated wave with a wavelength inversely proportional to the particle's momentum. The greater the momentum, the shorter the wavelength. At everyday scales, the wavelengths of matter waves are so absurdly small as to be undetectable. A moving baseball has a de Broglie wavelength smaller than a proton by many orders of magnitude. But for electrons, the wavelengths are on the scale of atoms, detectable. In 1927, Clinton Davison and Lester Germer at Bell Labs accidentally confirmed de Broglie's prediction. They were bouncing electrons off a nickel crystal and noticed an unexpected pattern in how the electrons scattered. The pattern was an interference pattern. Electrons were diffracting off the crystal lattice exactly as X-rays would. Electron waves. The wave-particle duality that had seemed like a peculiarity of light was a fundamental feature of all quantum objects. De Broglie received the Nobel Prize in 1929. Davison received it in 1937. The question of how one thing can be both a wave and a particle had produced, by the late 1920s, an entirely new physics. So that's the history. But what is a photon actually made of? That question is harder than it looks. When physicists say a photon is a particle, they don't mean it's like a tiny marble rolling through space. Marbles have size. They have a surface you could in principle touch. They're made of smaller things, atoms, which are made of electrons and nuclei, which are made of protons and neutrons, which are made of quarks. A photon has none of this structure. As far as anyone can tell, a photon has zero size. It's a point particle in the sense that it has no spatial extent. Or more precisely, it's not a particle in any intuitive classical sense at all. It's a quantum excitation of the electromagnetic field. To understand what that phrase actually means, you need to understand how quantum mechanics changed our picture of what fields are. Think about temperature. Temperature is a field in a simple, everyday sense. At every location in a room, there's a specific temperature. The temperature field fills the room continuously. Every point has a value. That value can vary from point to point. And the value changes over time as the room heats up or cools down. But the temperature field isn't a thing in itself. It's a property of the space. It doesn't have its own independent existence separate from the molecules that have that temperature. Electromagnetic fields are different. At every point in space, there's an electric field strength and a magnetic field strength. These are real physical quantities that exist independently of any charges or currents. An electromagnetic wave traveling through empty space carries real energy, real momentum, and real information. And there's nothing there except the oscillating field values themselves. The field is the substance. There is no substrate it lives in. Classical electromagnetism describes these fields as smooth and continuous. At every point in space, the field has a definite value. The energy of an electromagnetic wave can take any value. There's no minimum packet. Quantum mechanics changes this picture fundamentally. In quantum field theory, the electromagnetic field is quantized. Its energy content doesn't flow continuously. It exists in discrete minimum packets. Think of it this way. The electromagnetic field is somewhat like a string stretched between 2 points. The string can oscillate in different ways, different frequencies of oscillation. In classical physics, the string can have any amount of energy in each oscillation mode. You can put in a tiny bit of energy, or a large bit, or any continuous amount in between. In the quantum version, each oscillation mode can only have energy in discrete steps. 0 units, 1 unit, 2 units, 3 units, but nothing in between. 1 unit of energy in a given oscillation mode of the electromagnetic field is a photon. The photon is the field's minimum energy excitation. It's not a thing riding the field. It is what the field does when it has exactly 1 unit of energy in a particular mode. This is the key insight. A photon isn't made of anything smaller. There's no inner structure to discover, no subphoton components, no pieces rattling around inside. It's an irreducible unit of the electromagnetic field. In the framework of quantum field theory, which is the most complete and precisely tested theory of fundamental physics ever developed, all particles work this way. Electrons are excitations of the electron field. Quarks are excitations of the quark fields. The Higgs boson is an excitation of the Higgs field. The W and Z bosons, which carry the weak nuclear force, are excitations of the weak nuclear field. Gluons, which carry the strong nuclear force, are excitations of the gluon field. And photons are excitations of the electromagnetic field. The entire standard model of particle physics is a collection of quantum fields, each filling all of space, each capable of being in states of various energy. The particles we detect in experiments are the excitations of those fields. The fields are the fundamental things. The particles are what fields do when they're excited. This framework sounds abstract. But quantum field theory, and specifically the quantum field theory of photons and electrons, called quantum electrodynamics, produces the most precise predictions ever made in science. There's a quantity called the anomalous magnetic moment of the electron. It's usually written in physics papers as G-2 divided by 2. Quantum electrodynamics predicts this quantity. The prediction requires calculating the effects of all possible ways that virtual photons can interact with the electron, using diagrams called Feynman diagrams. The calculation has been carried to extremely high precision over decades of theoretical work. The current, theoretical prediction agrees with the best experimental measurement to more than 12 significant figures. To give you a sense of what 12 significant figures means, if you were predicting the distance between London and Moscow, 12 significant figures of accuracy would mean your prediction was correct to within a fraction of the width of a single atom. No other theory in the history of human science has achieved anything close to that level of precision. So when physicists say photons are excitations of the electromagnetic field, they are describing a framework that has been tested to an extraordinary depth. But accurate isn't the same as intuitive. The nature of a photon still defies common sense in ways that took decades of the 20th century to grapple with, and that still occupy philosophers and physicists today. Remember Young's double-slit experiment. If light is made of particles, a photon fired at a barrier with 2 slits should go through one slit or the other, not both. A particle has a definite trajectory. It takes one path. But when you do this experiment with single photons, firing them one at a time so there's no possibility of 2 photons interfering with each other, the interference pattern still builds up on the screen, dot by dot, hit by hit. Each individual photon leaves a single point-like mark when it hits the screen, particle-like. But over time, as thousands and then millions of individual photons arrive, those points accumulate into the alternating bright and dark bands of an interference pattern. Wave-like. Each individual photon somehow contributes to a pattern that only makes sense if the photon went through both slits. The interference pattern is proof of it. A pattern that arises from destructive and constructive interference can only come from something that took both paths and then interfered with itself. But if you place a detector at one of the slits to find out which slit the photon actually went through, the interference pattern vanishes. Every photon goes through one slit or the other. Two bands appear on the screen, one behind each slit. The interference is gone, not reduced. Gone. The act of determining the path eliminates the interference. The quantum mechanical explanation for this is the wave function. Before the photon is detected at the screen, its state is described by a wave function, a mathematical object that assigns a probability amplitude to every possible location and every possible path. The wave function isn't a description of our ignorance about where the photon is. It's a description of the photon's actual physical state. Before detection, the photon genuinely doesn't have a definite position or a definite path. It exists as a superposition of all possibilities, weighted by their probability amplitudes. The wave function extends through space and can go through both slits simultaneously. On the other side, the part of the wave function that went through the left slit and the part that went through the right slit overlap and interfere. In some regions, their amplitudes add together, resulting in high probability of the photon landing there. In other regions, their amplitudes cancel, resulting in near zero probability. This probability distribution is the interference pattern. When the photon is detected, the wave function collapses to a specific location. But where it lands is determined by the probability distribution built up by the interference. When you put a detector at one of the slits, you gain information about which path the photon took. The moment that information becomes available in principle, the wave function changes. It's no longer a superposition of both paths. It collapses to one path, and a wave function corresponding to one definite path produces no interference pattern. Two bands. No stripes. The universe appears to keep track of information. The mere existence of path information, whether or not anyone reads it, changes the physical outcome of the experiment. This is one of the most deeply disturbing facts in modern physics. It's at the heart of what's called the measurement problem in quantum mechanics. And nobody fully agrees on what it means. The Copenhagen interpretation, developed primarily by Niels Bohr and Werner Heisenberg in the 1920s, says that quantum objects don't have definite properties before they're measured. The wave function is complete. Measurement collapses the wave function. And asking what the photon was doing before you measured it is a meaningless question. The many worlds interpretation, developed by Hugh Everett in 1957, says the wave function never collapses. Every possible measurement outcome happens in different branches of a universal wave function. When you measure which slit the photon went through, you and the photon become entangled, and the universe splits into branches where you see each possible outcome. There's no collapse, just branching. Pilot wave theory, developed by Louis de Broglie and later completed by David Bohm, says particles have definite positions and trajectories at all times. They're guided by a real physical wave called the pilot wave. The apparent randomness of quantum measurements comes from ignorance of the particle's initial conditions, not from fundamental indeterminacy. These interpretations make identical predictions for all experiments. They differ on what the wave function means, whether it's a description of reality or our knowledge of reality. Whether quantum indeterminacy is fundamental or merely apparent. Physicists disagree on which interpretation is correct. Some think the question is meaningless. What matters is the mathematics, and the mathematics works. There's a version of the double-slit experiment called the quantum eraser that makes the situation even stranger. You place witch path detectors at both slits, so the interference pattern disappears. Then, downstream, after the photons have already hit the screen, you set up a way to erase the witch path information from the detector. When you erase the witch path information after the photon has already been detected, the interference pattern reappears. Specifically, it reappears in the sub-ensemble of detection events that correspond to photons whose witch path information was erased. The events that don't have their witch path information erased don't show the interference pattern. This is not a trick of the statistics. It's a genuine physical effect that has been confirmed in multiple laboratories. The behavior of the photon at the screen appears to depend on what happens to information about its path, even if that information is collected and then erased after the photon has already been detected. This is a deeply unsettling result for any classical or common-sense picture of reality. What we can say with confidence is that the photon is not a classical particle. It cannot be assigned a definite position and trajectory before measurement. Its behavior in experiments like the double slit is not due to ignorance or experimental imprecision. It's a fundamental feature of what the photon is. Now, back to the question of why a photon never stands still. The answer is built into the structure of special relativity and the properties that make a photon what it is. A photon's energy is determined by its frequency, through Planck's formula. Energy equals Planck's constant times frequency. Frequency, in the context of an electromagnetic wave, describes how rapidly the fields oscillate as the wave propagates. This oscillation is tied to the wave's propagation through space. It makes sense only for a wave that is moving. For a stationary oscillation, the relevant concept of frequency for a propagating photon doesn't apply. More fundamentally, consider what mass means in special relativity and why it matters so much for this question. Before Einstein, mass was just mass. The amount of stuff in an object. Newton's second law says force equals mass times acceleration. More massive objects are harder to accelerate. Less massive objects are easier. And the mass of an object was thought to be a fixed property, the same in all situations. Special relativity changed this picture completely. Einstein showed that mass and energy are not independent quantities. They're different aspects of the same thing. The relationship between them is given by what is probably the most famous equation in science. E equals mc squared. For an object at rest, all of its energy comes from its mass. A proton at rest, not moving, contains energy equal to its mass times the speed of light squared. That energy is real and has real consequences. Nuclear reactions convert a fraction of this rest mass energy to other forms. The energy released by a nuclear weapon and the energy produced by the sun through nuclear fusion come from the conversion of rest mass to other forms of energy. This rest mass energy is something every massive particle carries simply by existing. Even a stationary electron has energy because it has mass. But photons have no mass. Zero mass. Not a very small mass. Not a mass below current detection thresholds. Zero. And this has been tested with extraordinary care, because the consequences of even a tiny photon mass would be significant and detectable. If photons had mass, the electromagnetic force law would be modified. Instead of falling off as one divided by the square of the distance from a charge, the electric force would be modified at very long ranges by the photon mass. This is called the Yukawa modification, after the Japanese physicist Hideki Yukawa, who predicted in 1935 that massive force carriers would produce short-range forces. The strong nuclear force works this way. The fundamental force between quarks is mediated by massless gluons, but the residual force that binds protons and neutrons together inside a nucleus is mediated by massive particles called pions, and that residual force has a short range. The electromagnetic force is mediated by massless photons and has infinite range. If photons had mass, the electromagnetic force would fall off faster at large distances than it does. Precision measurements of the electric field around charged objects and careful studies of the magnetic fields of planets and the Sun constrain the photon mass to extraordinary precision. Observations of radio pulses from pulsars, spinning neutron stars that emit extremely regular pulses of radio waves, provide another constraint. If photons had mass, different frequency photons would travel at slightly different speeds. Lower energy photons would travel slightly more slowly than higher energy ones. Radio pulses, which contain a range of frequencies, would arrive spread out in time rather than as sharp pulses. The sharpness of observed pulsar timing places tight constraints on any energy dependence of photon speed, which in turn constrains the photon mass. Observations of gamma-ray bursts, which are among the most energetic events in the universe and produce photons across a huge range of energies, simultaneously, have also been used to set limits. If high-energy gamma-ray photons and low-energy optical photons emitted at the same moment arrived at different times, we'd see it. Over cosmological distances, even a tiny speed difference would accumulate into a detectable delay. No such delay has been found at the level of precision astronomers can measure. The current experimental upper bound on photon mass is somewhere around 10 to the minus 54 kilograms. The electron, the lightest known massive particle, has a mass of about 9 times 10 to the minus 31 kilograms. The upper bound on photon mass is roughly 23 orders of magnitude smaller than the electron mass. For all purposes that physics has been able to probe, the photon mass is exactly zero. And here's why that matters, for why photons can never stand still. In special relativity, every massive particle has what's called a rest frame, a reference frame in which the particle is stationary. You can always, in principle, accelerate yourself to match the speed of a massive particle and see it at rest. The particle has a definite speed relative to any given frame, and that speed can be reduced to zero by choosing the right frame. For massless particles, this is impossible. A fundamental consequence of special relativity is that the speed of light is the same in all reference frames. No matter how fast you're moving, no matter what direction you're moving in, a photon passing by you moves at exactly 300,000 kilometers per second relative to you. This is not an approximation. It's not that photons move very fast and are hard to catch. It's that the speed of light is a feature of space and time themselves, not of any particular source or observer. Einstein's special relativity is built on two postulates. First, the laws of physics are the same in all inertial reference frames. Second, the speed of light in vacuum is the same for all observers, regardless of the motion of the source or the observer. The second postulate means that a photon cannot be at rest in any reference frame. If it were at rest in one frame, it would be moving at different speeds in other frames, violating the second postulate. The only consistent solution is that photons always move at c in every reference frame simultaneously. This is strange. Nothing, in everyday experience, prepares us for it. If you're standing still and a car passes you at 100 kilometers per hour, and then you get in your own car and drive in the same direction at 80 kilometers per hour, the passing car seems to go by you at only 20 kilometers per hour. Velocities add. For massive objects moving slowly compared to light, this works fine. But for light, it breaks down completely. You cannot boost yourself into a frame where the photon is moving more slowly. No matter how fast you go, the photon is still moving away from you at exactly 300,000 kilometers per second. There is no rest frame for the photon, and a particle with no rest frame cannot be at rest. The photon moves at c, from the moment it's created to the moment it's absorbed, period. Now here's a consequence that follows directly from special relativity and is even harder to absorb. From the photon's perspective, if such a perspective were meaningful, the journey takes no time at all. Time dilation is one of the strangest and most verified consequences of special relativity. Moving clocks run slow. Specifically, a clock moving at speed v, relative to a stationary observer, ticks at a rate that is reduced by a factor called the Lorentz factor. The Lorentz factor is 1 divided by the square root of 1 minus v squared divided by c squared. At everyday speeds, v is so much smaller than c that the Lorentz factor is essentially 1. Your watch runs at the same rate whether you're sitting still or driving a car at 100 kilometers per hour. The difference is undetectable. But as v approaches c, the Lorentz factor grows without bound. At 99% of the speed of light, the Lorentz factor is about 7. Your clock ticks 7 times more slowly than a stationary observer's clock. At 99.9% of the speed of light, the Lorentz factor is about 22. At 99.999% of the speed of light, the Lorentz factor is over 1,000. At the speed of light itself, the Lorentz factor becomes infinite. An infinite Lorentz factor means a clock moving at c ticks infinitely slowly. 0 tick rate. Time, for an object moving at c, does not pass at all. For the photon, the entire journey from emission to absorption is instantaneous. A photon emitted in the core of a distant galaxy 8 billion years ago and detected by your eye tonight has not experienced any duration between those two events. 8 billion years of cosmic time, of stars forming and going out, of galaxies evolving, of the universe expanding, of a planet forming around a star and life evolving on it. All of that was happening while the photon was in transit. But for the photon, it was not in transit. There was no duration. Emission and absorption were the same instant, which is why I said there's no meaningful photon's eye view. There's no clock to tick. There's no subjective experience. There's no inside from which to observe anything. The photon exists only at the moments of its interactions with matter. Between those moments, it is, from its own non-existent reference frame, nothing. And yet here you are, experiencing time, catching photons that have been traveling for billions of years. The photon has no mass. It has no rest frame. It has no experience of time. And you have all three. Different in kind, not just different in degree. The photon carries something else that most people don't expect. Momentum. The classical formula for momentum is mass times velocity. A photon has 0 mass. 0 times anything is 0. So a photon should have no momentum. But this conclusion is wrong, and the reason it's wrong tells you something important about the limits of classical physics. The classical momentum formula is an approximation that works well for massive objects at low speeds. The complete, relativistically correct relationship between energy, momentum, and mass is more fundamental. It says, the square of the energy equals the square of the momentum times c squared plus the square of the mass times c to the fourth power. This is called the energy-momentum relation, and it works for everything. For a particle at rest with mass m, momentum is 0, and the equation gives energy equals mass times c squared. For a massless particle, the mass term vanishes entirely. What remains is energy equals momentum times c. Rearranging. Momentum equals energy divided by c. The photon's momentum is real, non-zero, and exactly equal to its energy divided by the speed of light. And this momentum transfers to whatever absorbs the photon. This is radiation pressure. It was predicted by Maxwell in the 1870s from his electromagnetic theory, and first measured experimentally by Pyotr Lebedev in Russia in 1900, and independently by Ernest Nichols and Gordon Hull in America in 1901. They shone light on a delicate suspended mirror and measured the tiny deflection caused by the pressure of the light. It's very small. At Earth's distance from the Sun, the radiation pressure of sunlight is about 4.5 micronewtons per square meter. To give you a sense of scale, a micronewton is 1/1,000,000th of a newton, and a newton is roughly the weight of a small apple. So 4.5 micronewtons is about 4.5 millionths of the weight of a small apple spread across 1 square meter. Tiny. But it's there. It's real. And for spacecraft, over the course of months and years, it accumulates. The force is continuous. The probe is always being pushed. And in the microgravity of interplanetary space, where there's no atmosphere to create drag, even a tiny continuous force changes the trajectory over time. Engineers who navigate spacecraft have to account for radiation pressure in their trajectory calculations. The navigation team for the Cassini mission at Saturn, which operated for 13 years from 1997 to 2017, had to account for solar radiation pressure consistently. So did the teams for every other deep space probe. Ignore it, and your spacecraft ends up somewhere other than where you planned. There's a famous early example of this going wrong: the Pioneer anomaly. The Pioneer 10 and 11 spacecraft, launched in 1972 and 1973 respectively, were tracked by radio signals for decades as they traveled out of the solar system. When scientists analyzed their trajectories with extreme precision, they found a tiny but persistent deviation from the expected path. The spacecraft were being accelerated slightly toward the Sun, more than gravity alone could account for. This anomaly persisted for over 30 years and generated considerable interest as a possible sign of new physics. The resolution, worked out in detail in 2012 using improved thermal models, turned out to be radiation pressure from the spacecraft's own heat. The spacecraft generated power using radioisotope thermoelectric generators, which produced waste heat. That heat radiated outward, preferentially from one side of the spacecraft. Infrared photons carry momentum, just like visible light photons. The tiny asymmetric push from those photons, accumulated over decades, explained the anomaly entirely. No new physics required. Just photon momentum, meticulously computed. Solar sails take the concept of photon momentum to its logical conclusion. If light can push a spacecraft, why not design a spacecraft that's mostly sail, the way a sailing ship is mostly sail? The more area you present to the sunlight, the harder the push. The Japanese Icaros spacecraft, launched in May 2010, deployed a square reflective sail, 14 meters across and just 7.5 micrometers thick. For comparison, a human hair is about 70 micrometers thick. The sail was 10 times thinner than a human hair. By the end of 2010, mission scientists had confirmed that solar radiation pressure was measurably accelerating the spacecraft, validating the concept. The Planetary Society, a space advocacy organization, launched their own solar sail demonstration mission called LightSail 2 in June 2019. It successfully used solar radiation pressure to raise its orbit around Earth. A photon with no mass, exerting a force with no contact, changing the orbit of a spacecraft. The photon's momentum also matters at the scale of individual atoms. When an atom absorbs a photon, it gains the photon's momentum as well as its energy. The atom receives a tiny kick in the direction the photon was traveling. When it re-emits a photon, it recoils in the opposite direction. This is the basis of laser cooling. Shine a laser at a cloud of atoms from the direction opposing their motion. The Doppler effect shifts the frequency of the laser light as seen by moving atoms. Atoms moving toward the laser source see the laser light blue shifted to higher frequency. If the laser is tuned carefully, this blue shifted frequency matches an absorption line of the atom. The atoms moving toward the laser absorb photons and receive momentum kicks that slow them down. Atoms, moving away from the laser, see the laser light redshifted, shifted to lower frequency, away from the absorption line, so they're less likely to absorb. The net effect is a force that selectively slows atoms that are moving toward the laser. Apply lasers from all 6 directions in 3-dimensional space, and you slow atoms moving in any direction. The temperature of a gas is directly related to the average kinetic energy of its atoms, which is related to how fast they're moving. Slow the atoms, and you cool the gas. Laser cooling can bring atoms to within a millionth of a degree of absolute zero, temperatures that are unachievable by any other method. Stephen Chu, Claude Cohen-Tanouji, and William Phillips developed laser cooling techniques through the 1980s. All 3 received the Nobel Prize in Physics in 1997. Laser cooling is now the starting point for some of the most precise instruments ever built. The atomic clocks used for GPS satellites, for comparison, are accurate to about 1 second in 300 million years. The most advanced optical lattice clocks, which use laser-cooled atoms, are accurate to about 1 second in 15 billion years, longer than the current age of the universe. If you ran 2 of these clocks for the age of the universe, they disagree by less than a second. They achieve this because laser-cooled atoms, moving so slowly that relativistic corrections become dominant, can be made into the most stable frequency references ever constructed. All of this from the momentum of photons. Now, photons are bosons. Every fundamental particle falls into one of 2 categories based on a quantum property called spin. Spin is an intrinsic form of angular momentum that particles carry as a fundamental quantum attribute. It's not actual physical rotation, though it has some mathematical properties similar to rotation. It's just something particles have, like mass, or charge. Particles with half-integer spin, like electrons with spin 1/2, and quarks, also with spin 1/2, are called fermions. Particles with integer spin, including photons with spin 1 and the Higgs boson with spin 0, are called bosons. This classification has enormous consequences. Fermions obey the Pauli exclusion principle. No two fermions can simultaneously occupy the same quantum state. The same energy level, the same position, the same momentum, the same spin direction, all identical in all their quantum numbers. The Pauli exclusion principle forbids it. If two electrons try to be in the same quantum state, the laws of quantum mechanics simply don't allow it. This is not a consequence of any force pushing the electrons apart. It's a fundamental feature of what fermions are. The consequences are foundational to the existence of matter as we know it. In an atom, electrons fill energy levels from the bottom up. The first energy level has room for two electrons, one with spin up and one with spin down. Once both spin states are occupied, the Pauli exclusion principle prevents any more electrons from entering that level. The next electron must go into the second energy level. This filling up of levels determines the electronic structure of atoms, which determines their chemical properties. An element's position in the periodic table and its chemical behavior are determined by how many electrons it has and how those electrons are arranged in levels according to the Pauli exclusion principle. Without the exclusion principle, all electrons would fall into the lowest energy level. Atoms would not have the shell structure that makes chemistry possible. Molecules would not form as they do. You would not exist. Bosons play by different rules entirely. Any number of bosons can occupy the same quantum state simultaneously. There's no exclusion. In fact, bosons don't just permit occupation of the same state. They actively encourage it. The quantum mechanical probability of a boson entering a particular state is enhanced when other bosons are already in that state. The more bosons in a state, the more likely the next boson is to join them. For photons, this bosonic tendency to cluster in the same state is the physical principle behind the laser. A laser produces photons, all in exactly the same quantum state. Same frequency, same direction, same polarization, same phase. Coherent light. The process works like this. You start with a medium, a gas, or a crystal, or a semiconductor, in which some atoms have been pumped into an excited energy state. An excited atom can emit a photon by dropping to its ground state. If it emits spontaneously, the photon goes in a random direction with a random phase. That's incoherent light, like a light bulb. But if a photon of exactly the right frequency passes through the excited medium, it can trigger the excited atom to emit a second photon. And because of the bosonic nature of photons, this stimulated emission produces a photon in exactly the same quantum state as the triggering photon. Same frequency, same direction, same phase. The two photons then travel together through the medium. Each of them can trigger another stimulated emission. 4 photons, all identical. Then 8. Then 16. The photon population in that specific quantum state grows exponentially. This is called stimulated emission. The laser gets its name from it. Light amplification by stimulated emission of radiation. The laser was first demonstrated by Theodore Maiman in 1960 using a ruby crystal as the medium. The flash lasted about 1 millisecond. It was the first coherent beam of light ever produced. In the years that followed, physicists developed lasers in a vast range of media. Gas lasers, using mixtures like helium-neon, produced stable, continuous beams suitable for precision measurement. Carbon dioxide lasers produced powerful infrared beams suitable for industrial cutting and welding. Dye lasers, using organic dyes dissolved in solution, could be tuned across a wide range of frequencies, making them useful for spectroscopy. Semiconductor lasers, using the quantum properties of semiconductor junctions, could be made extraordinarily compact. The laser diode, in a DVD player, is smaller than a grain of rice. It operates on the same physical principle as a 4-kilometer laser interferometer. The technology of coherent light, unlocked by understanding the bosonic nature of photons, transformed modern life so completely that it's essentially invisible. It's inside the barcode scanners at the supermarket. It's inside the pointer in a classroom. It's inside the sensors that guide autonomous vehicles. It reads data from optical discs. It corrects your vision through laser eye surgery. It performs bloodless surgery on internal organs through fiber optic guides. It aligns the lasers of particle accelerators. It measures distances to the millimeter from satellites. Without an understanding of what photons are and how they behave as bosons, none of it exists. The technological consequences have been sweeping. Medical applications include laser surgery for eyes, cancer treatment, dental procedures, and dermatological applications. Industrial applications include laser cutting and welding of metal, precision measurement and alignment tools, and the lithographic systems used to manufacture computer chips. The circuits on a modern semiconductor chip are printed using extreme ultraviolet laser light with wavelengths of 13.5 nanometers. A nanometer is 1/1000th of a meter. Communications applications include the fiber optic networks that carry most of the world's internet traffic. Light pulses from laser diodes travel down hair-thin glass fibers at speeds close to C, carrying terabits of data per second. Every time you load a web page or send a message, photons are doing the work. Scientific applications include interferometers, sensitive enough to detect the ripples in space-time from merging black holes billions of light-years away. The LIGO detectors that first observed gravitational waves in September 2015 use laser interferometry at the heart of their measurement. The two LIGO arms, each 4 kilometers long, measure changes in length smaller than 1/10,000th the diameter of a proton. They do this by comparing the travel times of laser photons sent down the two arms. When a gravitational wave passes through, it stretches space in one direction and compresses it in the other, changing the arm lengths by an imperceptible amount. The laser detects it. Something that warped space-time billions of light-years away left its signature in the interference pattern of photons in Louisiana and Washington state. The bosonic nature of photons also enables something even more extreme than a laser. When identical bosons are cooled to temperatures close to absolute zero, they can collapse into the same quantum state collectively. All of them. Every single particle in the system occupying the same ground state simultaneously. This state of matter is called a Bose-Einstein condensate. It was predicted by Einstein and the Indian physicist Satyendra Nath Bose in the 1920s. It wasn't experimentally realized until 1995, when Eric Cornell and Carl Wieman at the University of Colorado created a condensate from rubidium atoms, and Wolfgang Ketterle at MIT created one from sodium atoms. In a Bose-Einstein condensate, thousands or millions of atoms are in exactly the same quantum state. The condensate behaves as a single quantum object, governed by a single wave function, even though it's macroscopic, visible in some cases to the naked eye. The condensate can be held in place, shaped, split, and interfered with in ways that look more like manipulating a quantum wave than a collection of individual particles. Cornell, Wieman, and Ketterle received the Nobel Prize in Physics in 2001. Photons can also form condensates. In 2010, Jan Kleyers and colleagues at the University of Bonn demonstrated that photons could be trapped and thermalized in a two-dimensional optical microcavity, allowing them to accumulate in a single ground state of the cavity. A photon Bose-Einstein condensate, a macroscopic quantum state of light. The bosonic nature of photons, the fact that they can pile into the same quantum state without restriction, and in fact preferentially do so, is not a subtle secondary property. It underlies most of the technology that defines modern civilization. The vacuum. In classical physics, a vacuum is the absence of everything. No particles, no fields, no energy, pure nothingness. Quantum field theory disagrees. The vacuum, in quantum field theory, is the lowest energy state of all quantum fields simultaneously. And lowest energy doesn't mean zero energy. The Heisenberg uncertainty principle places fundamental constraints on how precisely any physical quantity can be defined. The version relevant here involves energy and time. The product of the uncertainty in energy and the uncertainty in the time over which you measure that energy must always be greater than or equal to Planck's constant divided by 4 times pi. This fundamental limit means you cannot have a state where the energy is precisely zero for any extended period of time. Perfect zero energy, known exactly and maintained indefinitely, would require a time measurement of infinite duration, which also violates the uncertainty principle in another way. The consequence is that all quantum fields, including the electromagnetic field, fluctuate at every point in space. The electric and magnetic field values are not precisely zero, even in a perfect vacuum with no photon sources anywhere. They fluctuate randomly, continuously, everywhere, at all times. These are vacuum fluctuations, zero-point fluctuations, and they have real, measurable consequences. There's a deeper point here about what the Heisenberg uncertainty principle actually means. The Heisenberg uncertainty principle doesn't just affect our ability to measure things. It describes what the physical world is actually like. Before quantum mechanics, the assumption underlying all of physics was that the world had a definite state at every moment, even when we didn't know it. Particles had exact positions and exact momenta. Fields had exact values at every point. Our ignorance was a practical limitation, not a fundamental one. Quantum mechanics overturned this completely. The uncertainty is not in our instruments or our knowledge. It's in the physical system itself. A photon does not have a definite frequency and a definite emission time simultaneously. A photon does not have a definite position and a definite momentum simultaneously. This isn't because we can't measure both precisely enough. It's because both don't simultaneously have definite values. The vacuum fluctuates, not because we're unable to prepare it in a perfectly zero energy state. It fluctuates because perfect zero is forbidden by the mathematics of quantum mechanics, which accurately describes what the universe actually does. Virtual photons are real consequences of this irreducible uncertainty. They're not a useful fiction. They're the mechanism by which the electromagnetic vacuum's unavoidable fluctuations manifest as forces, energy shifts, and pressures between surfaces. The most direct and dramatic evidence is the Casimir effect. In 1948, the Dutch physicist Hendrik Casimir was working at the Philips Research Laboratories in Eindhoven. He was studying the properties of colloidal suspensions, tiny particles in solution. These particles are coated with molecules that prevent them from clumping together. Casimir was trying to calculate the forces between these coatings. During a conversation with Niels Bohr, he described his calculations. Bohr suggested that van der Waals forces, which are the forces between molecules due to their fluctuating electric dipoles, might be relevant. Casimir took this idea and extended it. He considered what would happen if you had two perfectly flat, perfectly conducting metal plates placed very close together in a perfect vacuum. Classical electrostatics says there should be no force between them if they carry no charge. But vacuum fluctuations of the electromagnetic field create a real pressure. The argument goes like this. In the empty space between the plates, the vacuum fluctuations of the electromagnetic field are constrained. Only electromagnetic modes whose wavelengths fit an integer number of half wavelengths into the gap can exist between the plates. Other modes are geometrically excluded. Outside the plates, in the surrounding space, all modes are available without restriction. This means there are more modes of vacuum fluctuation outside the plates than between them. Each mode carries a tiny amount of zero-point energy. More modes outside than inside means more energy pressure pushing inward from outside than from inside pushing outward. The net effect is that the plates are pushed together. Casimir calculated the force precisely. It falls off as the inverse fourth power of the separation between the plates. Halve the separation, and the force increases by a factor of 16. At very small separations, the force becomes large. At a separation of 10 nanometers, roughly 100 atom diameters, the Casimir pressure between two ideal metal plates is approximately 1 atmosphere. The full atmospheric pressure you experience at sea level, generated by virtual photons. Particles that technically don't exist in the conventional sense. The Casimir effect was not measured experimentally until nearly 50 years after Casimir predicted it. It required very flat, very clean surfaces and very precise measurement techniques. In 1997, Steve Lamoureux at the University of Washington, later working at Los Alamos, used a torsional balance and carefully prepared surfaces to measure the Casimir force for separations ranging from about half a micrometer to several micrometers. His measurements matched Casimir's predictions to within 15%. Subsequent, more precise measurements have done better. The vacuum is not empty. The space between your hands right now contains fluctuating electromagnetic fields. Virtual photons, popping into and out of existence everywhere. You are swimming in a sea of zero-point electromagnetic fluctuations that you cannot see and cannot feel and cannot avoid. Virtual photons are also the mechanism by which the electromagnetic force works. When two electrons repel each other, no ball is thrown and no string is pulled. The force is mediated by the exchange of virtual photons. One electron emits a virtual photon. The other absorbs it. The photon carries momentum between them, resulting in the force that pushes them apart. This isn't a metaphor. In quantum electrodynamics, this exchange of virtual photons is the literal mechanism of electrostatic repulsion. Richard Feynman developed a beautiful, diagrammatic way to represent these interactions, now called Feynman diagrams. Each diagram represents one possible way for a process to occur, involving a specific number of virtual photon exchanges and other quantum events. The actual probability of the process is obtained by summing over all possible diagrams, which corresponds to a mathematical procedure called perturbation theory. The calculation of something as simple as one electron scattering off another involves an infinite number of diagrams, but the contributions get smaller and smaller, and the sum converges to a precise answer, an answer that can be checked against experiment, every time, to extraordinary precision. Feynman, Julian Schwinger, and Sine Itaro Tomonaga received the Nobel Prize in Physics in 1965 for developing quantum electrodynamics. Feynman called it the jewel of physics. After a lifetime spent working on problems at the frontier of theoretical physics, he thought quantum electrodynamics was the most beautiful and precise theory humanity had ever produced. The vacuum is alive with virtual photons. They press things together. They pull electrons around inside atoms, shifting energy levels in ways you can calculate and measure. This last effect has a name: the Lamb shift. In 1947, Willis Lamb and Robert Rutherford at Columbia University measured the energy levels of hydrogen with unprecedented precision. The Dirac equation, which had been the definitive quantum mechanical description of the electron since 1928, predicted that two specific energy levels in hydrogen, called the 2s1/2 level and the 2p1/2 level, should be exactly the same. They weren't. The 2s1/2 level was shifted slightly higher than the 2p1/2 level. The difference was tiny, about 1 gigahertz in frequency terms, but it was real and reproducible. The explanation required quantum electrodynamics. Virtual photons, popping into and out of existence around the electron, perturb its energy levels. The perturbation is different for the 2s and 2p states because of their different spatial distributions. When Hans Bethe heard Lamb present the result, he calculated the expected shift on a train ride from New York to Ithaca. The answer matched the measurement. Lamb received the Nobel Prize in Physics in 1955 for this discovery. The Lamb shift is a direct experimental signature of the quantum vacuum, of the sea of virtual photons that permeates all of space. They make two electrons repel each other. They are everywhere. They never stop. And they exist because the quantum vacuum cannot be perfectly still. The sun. Bring this back to something concrete. Every second, the sun's core converts roughly 600 million tons of hydrogen into helium through nuclear fusion. 4 protons fuse into one helium nucleus. The helium nucleus has slightly less mass than the 4 protons did separately. The difference, about 4 million tons per second, is converted to energy following E equals mc squared. That energy starts its journey as gamma-ray photons produced in the fusion reactions. But those photons don't travel directly to you. The solar interior is extraordinarily dense. The core has a density about 15 times that of lead. Temperatures in the core reach about 15 million kelvins. In those conditions, the plasma is so dense that a photon is absorbed by a particle almost immediately after being emitted. The mean free path, the average distance a photon travels before being absorbed and re-emitted, is roughly 1 centimeter in the deepest parts of the core, sometimes less. To travel outward, through the roughly 700,000 kilometers of solar interior to the photosphere, the visible surface, a photon has to undergo this absorption and re-emission cycle an astronomically large number of times. Each re-emission sends the photon in a random direction. The photon isn't making steady progress outward. It's doing a random walk through the plasma, sometimes heading outward, sometimes inward, sometimes sideways. The time it takes to escape by this random walk depends on the density and opacity of the material. Careful calculations using detailed solar models give estimates typically in the range of 10,000 to 100,000 years for the average photon. Some estimates go higher. This is the photon diffusion timescale, and it's been calculated by solar physicists over many decades. The photon that entered this random walk when humans were first developing agriculture may only now be reaching the solar surface. At the photosphere, the density drops sharply. The plasma becomes transparent. Photons that reach this layer can escape. They launch outward into space. And, from the photosphere, traveling at 300,000 kilometers per second, it takes a photon approximately 8 minutes and 20 seconds to cross the 150 million kilometers to Earth. 8 minutes and 20 seconds, after potentially tens of thousands of years of random walking through the sun. The energy you're receiving right now from sunlight, if you're near a window, has been in transit since long before recorded history began. When that photon reaches your eye, it triggers a cascade of biochemistry. The proteins in your rod and cone cells, called opsins, contain a molecule called retinol. Retinol is a form of vitamin A. It sits in the binding pocket of the opsin protein in a bent configuration called the 11-cis form. When retinol absorbs a photon of visible light, it changes shape from the bent 11-cis configuration to a straight all-trans configuration. This molecular shape change, called photoisomerization, happens within 200 femtoseconds of absorption. A femtosecond is 1/millionth of 1/billionth of a second. It is one of the fastest biochemical reactions known. This shape change triggers the opsin protein to change configuration as well. That activated opsin then interacts with a molecule called transducin. Transducin activates phosphodiesterase. Phosphodiesterase breaks down a messenger molecule called cyclic GMP. The reduction in cyclic GMP closes ion channels in the photoreceptor cell membrane. That change in ion flow produces a change in the electrical potential across the photoreceptor cell membrane. That electrical signal travels along the optic nerve to your brain's visual cortex. Each step in that chain amplifies the signal. One absorbed photon activates one retinol molecule. One activated retinol molecule activates one opsin. One activated opsin activates about 800 transducin molecules. Each transducin activates one phosphodiesterase. Each phosphodiesterase breaks down about 800 cyclic GMP molecules per second. The signal amplification from a single photon to a detectable electrical change in the cell involves a cascade that amplifies the original signal by a factor of roughly 100,000. One photon, 100,000 times amplified. Enough to register. Your brain processes the signals from millions of photoreceptors simultaneously and constructs your visual perception of the world. Every visual experience you've ever had was built from photons arriving and being absorbed. The human retina contains about 130 million photoreceptors. About 6 to 7 million are cone cells, responsible for color vision in bright light. About 120 to 125 million are rod cells, responsible for vision in dim light. The rod cells are extraordinarily sensitive. Under ideal conditions, a dark adapted rod cell can respond to a single photon. 1 photon. The minimum possible quantity of visible light. Your eye, at its most sensitive, is operating at the quantum limit of light detection. This was confirmed in the 1940s by Selig Hecht, Simon Schleyer, and Maurice Pirenne, who demonstrated that human observers could detect flashes containing as few as 5 to 7 photons hitting the retina. Since not every photon that hits the retina triggers a photoreceptor response, this was consistent with single photon detection at the cellular level. More recent experiments using quantum light sources have confirmed and refined this result. The cone cells contain 3 different types of opsin, each sensitive to a different range of frequencies. One type is most sensitive to long wavelengths, around 564 nanometers, corresponding to red-orange light. One to medium wavelengths, around 534 nanometers, corresponding to green light. And one to short wavelengths, around 420 nanometers, corresponding to blue-violet light. Your brain compares the signals from these 3 types of cone cells and constructs your perception of color. The entire richness of your color vision, the billions of colors you can distinguish, comes from comparing signals from these 3 types of photoreceptors, each responding to a different range of photon frequencies. Beyond visible light, photons span a range of frequencies so enormous that the highest is roughly 10 to the 24th power times the lowest. That's 1, followed by 24 zeros. Radio waves at the bottom, from a few thousand hertz to a few hundred megahertz. Microwaves from a few hundred megahertz to a few hundred gigahertz. Infrared from a few hundred gigahertz to a few hundred terahertz. Visible light in a narrow band around 400 to 750 terahertz. Ultraviolet from about 750 terahertz to 30 petahertz. A petahertz is 10 to the 15th hertz. X-rays from 30 petahertz to 30 exahertz. An exahertz is 10 to the 18th hertz. And gamma rays above 30 exahertz. All of these are the same particle. A radio photon from a commercial broadcast station and a gamma ray photon emitted in a nuclear reaction are both excitations of the same electromagnetic field. They obey the same physics. They travel at the same speed. They interact with matter through the same electromagnetic force. The only difference is energy. Radio photons carry so little energy that you can absorb millions of them every second with no biological effect. Gamma-ray photons carry enough energy to ionize atoms and break molecular bonds directly. A few thousand gamma-ray photons in a critical organ can cause serious damage to biological tissue. The same particle, at different energy scales, with consequences that range from the broadcasts filling your living room to the radiation hazards in a nuclear reactor. Astronomers use photons across the entire electromagnetic spectrum to study the universe. Radio telescopes collect photons with wavelengths measured in meters. They've been used to map the structure of our galaxy, discover pulsars, and detect the signals from distant quasars. Infrared telescopes like the James Webb Space Telescope observe photons that have been redshifted by the expansion of the universe, allowing them to see galaxies as they were just a few 100 million years after the Big Bang. X-ray telescopes, which have to be placed in space because Earth's atmosphere absorbs X-ray photons, observe energetic phenomena like gas falling into black holes, the hot plasma in galaxy clusters, and neutron star collisions. Gamma-ray telescopes observe the most energetic events in the universe, including gamma-ray bursts that for a fraction of a second can outshine an entire galaxy. Every observation in astronomy, from the earliest naked-eye observations of planets to the most sophisticated modern space telescopes, is the collection of photons. The universe is known to us only through the photons it sends. Spectroscopy is the primary tool through which astronomers extract information from those photons. When atoms absorb or emit photons, they do so at specific frequencies determined by the allowed energy transitions of their electrons. Every element has a unique fingerprint, a unique set of frequencies it will absorb or emit. These fingerprints appear as dark absorption lines in the spectrum of starlight. The light from a star passes through the cooler outer layers of the star's atmosphere on its way out, and atoms in those outer layers absorb photons at specific frequencies, leaving dark gaps in the spectrum. By analyzing which frequencies are absorbed, astronomers can determine which elements are present in the star and in what proportions. This technique was pioneered in the 19th century. Joseph von Fraunhofer catalogued hundreds of dark lines in the solar spectrum in the 18-teens, though he didn't know what caused them. It wasn't until the 1860s that Gustav Kirchhoff and Robert Bunsen established that specific spectral lines were the fingerprints of specific elements. Bunsen invented the Bunsen burner, in part to create a clean, colorless flame that wouldn't add its own spectral lines when testing the emission of different materials. Through spectroscopy, the chemical composition of the sun and stars became knowable from Earth. No sample was required. No spacecraft was sent. Only photons. And because photons from distant sources are redshifted by the expansion of the universe, their spectral lines shift to longer wavelengths in a predictable way. By measuring how far the lines have shifted from their known laboratory positions, astronomers can determine how fast a galaxy is receding and at what distance. The entire edifice of cosmology, our understanding of the size and expansion of the universe and its large-scale structure, rests on measuring the redshifts of photons from billions of galaxies. Edwin Hubble's discovery in 1929 that distant galaxies were receding and that more distant ones were receding faster was made by measuring the redshifts of their spectral lines. Photons arriving from those galaxies carried information about the speed of their sources, encoded in the shift of their spectral fingerprints. From this, Hubble inferred that the universe was expanding. From this inference came the Big Bang. All of it, every step, from photons. Photons from the cosmic microwave background are filling all of space right now. Every cubic centimeter of space in the observable universe contains, on average, about 411 of these photons. They're in the space inside your home, in the air around you. They pass through you continuously. They're the photons of the first light that ever traveled freely through the universe. In the first minutes after the Big Bang, the universe was an extraordinarily hot, dense plasma. All of ordinary matter was ionized. Electrons were free, not bound to nuclei. Free electrons scatter photons very efficiently. The plasma was opaque. Photons could not travel any significant distance without being absorbed and re-emitted. The universe was a fog of light and matter, all in thermal equilibrium with each other. This continued for roughly 380,000 years. Then, the universe cooled to about 3,000 kelvins. At this temperature, electrons and protons could combine to form neutral hydrogen atoms without immediately being ionized again, in a period that lasted for a few thousand years. Essentially, all the free electrons combined with protons. The plasma became a neutral gas. And neutral hydrogen doesn't scatter photons nearly as efficiently as free electrons do. Suddenly, the universe became transparent. The photons that had been bouncing around, absorbed and re-emitted millions of times, were suddenly free. They streamed outward in all directions and have been traveling freely ever since. In the intervening 13.4 billion years, the universe has expanded by a factor of about 1,100. The photons have been stretched by this expansion. Their wavelengths have grown by a factor of 1,100. What started as thermal radiation at 3,000 kelvins is now thermal radiation at about 2.7 kelvins. Microwaves. These microwaves were first detected by Arno Penzias and Robert Wilson at Bell Telephone Laboratories in New Jersey in 1964. They were using a large radio antenna that had been built for communications, satellites, and noticed an unexplained background noise that came from every direction in the sky with equal intensity. After ruling out every possible instrumental explanation, including checking for pigeons nesting in the antenna, they concluded the signal was real and cosmological. They had no idea what they'd found. Robert Dick and James Peebles at Princeton, working independently on a theoretical prediction of the microwave background, heard about the Bell Labs results and immediately understood. Penzias and Wilson had discovered the cosmic microwave background, the oldest light in the universe, the echo of the Big Bang. They received the Nobel Prize in Physics in 1978. The cosmic microwave background is not perfectly uniform. It has tiny variations, temperature differences of about 1 part in 100,000, that encode detailed information about the state of the early universe. These are the imprints of tiny density fluctuations in the early universe. Regions that were slightly denser than average attracted more matter over time, eventually forming the clusters and superclusters of galaxies we see in the large-scale structure of the universe. The patterns in the cosmic microwave background are the seeds of all the cosmic structure that exists today. The COBE satellite, launched in 1989, made the first all-sky maps of the microwave background with sufficient sensitivity to detect these variations. George Smoot and John Mather led the team that made this measurement. They received the Nobel Prize in Physics in 2006. Subsequent missions have improved the measurements. The WMAP satellite, operating from 2001 to 2010, and the European Space Agency's Planck satellite, operating from 2009 to 2013, mapped the microwave background with increasing angular resolution and temperature sensitivity. From these maps, cosmologists have extracted precise values for the age of the universe, 13.8 billion years. The geometry of space, which turns out to be flat to high precision. The density of ordinary matter, about 5% of the total energy content. The density of dark matter, about 27%. And the density of dark energy, about 68%. All of this information from photons. Ancient photons that have been traveling since the universe was 380,000 years old. The oldest light in the universe is everywhere. The universe is still glowing with the thermal radiation of its own formation. Photons have also revealed one of the most unexpected discoveries in the history of cosmology. In the late 1990s, two independent teams were using observations of distant supernovae to measure the expansion rate of the universe. Supernovae of a particular type, called Type Ia supernovae, are standard candles. Their peak brightness is known, so by measuring how dim they appear, you can determine how far away they are. By also measuring the redshift of the supernova's light, how much the photons have been stretched by the expansion of space, you can determine the recession velocity of the galaxy that hosted the supernova. The two teams, one led by Saul Perlmutter at Lawrence Berkeley National Laboratory and the other led by Brian Schmidt at the Australian National University and Adam Rees at Harvard, were comparing how the expansion rate changed over time. Everyone expected to find that the expansion was slowing down. Gravity should be pulling matter together and decelerating the expansion. Both teams found the opposite. The expansion of the universe is accelerating, not decelerating. The supernovae at the greatest distances were fainter than they should have been if the expansion were uniform or decelerating. Their photons had traveled through a universe that was expanding faster and faster. This result implied that some form of energy permeates empty space and drives the acceleration. It was given the name dark energy. Its nature remains entirely unknown. Perlmutter, Schmidt, and Reis received the Nobel Prize in Physics in 2011. The discovery that the universe's expansion is accelerating was made by measuring the brightness and color of photons from exploding stars billions of light-years away. Photons carry information about the large-scale fate of the universe. Now, the frontier. Quantum entanglement is where photons are doing something genuinely new. When two photons are produced together in certain processes, their quantum states are correlated in ways that have no classical analog. The most commonly used process to produce entangled photons is called spontaneous parametric down-conversion. A photon passes through a specially prepared non-linear crystal. The crystal has quantum mechanical properties that give it a small probability of absorbing the incoming photon and producing two lower energy photons in its place. Energy is conserved. The two output photons together carry the same energy as the input photon, and momentum is conserved. The two output photons travel in different directions that together preserve the original momentum. But quantum mechanically, these two photons are produced in a single process. Their quantum states are correlated. If the input photon has no definite polarization, which can be arranged, then the two output photons are produced in an entangled state where neither has a definite polarization individually. They don't secretly have definite polarizations that we just don't know. The polarizations are genuinely indeterminate. But the two photons' polarizations are correlated. Measure the polarization of one along any axis, and you immediately know what the polarization of the other will be when measured along any axis. The correlations are specified by quantum mechanics precisely. This sounds like the photons might be secretly carrying predefined polarizations, like hidden labels. They're both heading to separate detectors, and the labels say what each detector will find. That would be a classical explanation. Einstein favored this kind of explanation. He thought quantum mechanics was incomplete, that it was a statistical description of some underlying reality with definite properties. In 1935, he wrote a famous paper with Boris Podolsky and Nathan Rosen exploring this, which is known as the EPR paradox. They argued that the correlations between entangled particles implied either that quantum mechanics was incomplete, missing some hidden variables, or that measuring one particle could instantly affect a distant particle, which they called spooky, action at a distance, and dismissed as impossible. Einstein believed quantum mechanics was incomplete. In 1964, the Northern Irish physicist John Bell showed that Einstein's hidden variable scenario makes specific, testable predictions. Bell derived mathematical inequalities. If the photons carry hidden variables, pre-programmed classical information about how they'll respond to any measurement, then the correlations between them are bounded. There's a maximum strength to the correlations that any hidden variable theory can produce. Quantum mechanics predicts that entangled photons will produce correlations stronger than this bound. This was testable. Alain Aspect and colleagues at the Institut d'Optique in Paris ran the decisive experiments between 1980 and 1982. They produced pairs of entangled photons from calcium atoms and measured their polarizations along randomly chosen axes. The correlations they found violated Bell's inequalities. The quantum mechanical prediction was confirmed. Classical hidden variables were ruled out. Over the following decades, experimentalists worked to close technical loopholes in these tests. One loophole is called the locality loophole. If the detector settings aren't chosen independently fast enough, a classical signal traveling between the detectors could carry the information needed to produce the observed correlations without entanglement. Another is the detection loophole. If only a fraction of the photons are detected, perhaps only the ones with special properties get through, the observed correlations might not represent the full ensemble. In 2015, 3 groups independently performed loophole-free Bell tests. One at Delft University of Technology in the Netherlands, using entangled nitrogen vacancy centers in diamond rather than photons. One at NIST in Boulder, Colorado, using entangled photons. And one at the University of Vienna, also using photons. All 3 confirmed that Bell's inequalities are violated. None of the loopholes could explain the results. Classical hidden variables are ruled out definitively. The universe is not locally realistic in the sense Einstein hoped. Physical properties of quantum particles do not have definite values before they're measured. Distant entangled particles have correlations stronger than any classical explanation allows. Alain Aspect, John Clauser, and Anton Zeilinger received the Nobel Prize in Physics in 2022 specifically for these contributions. The experimental evidence for quantum entanglement is now beyond question. The question of what it means for our understanding of reality is still being actively debated. Quantum cryptography uses entangled photons to guarantee the security of communications in a way that no classical system can match. The BB-84 protocol, developed by Charles Bennett and Gilles Brassard in 1984, uses quantum states of individual photons to distribute cryptographic keys. The security relies on the fact that measuring a quantum state disturbs it irreversibly. Any eavesdropper who intercepts the photons must measure them, and that measurement leaves a detectable trace in the photon statistics. The communicating parties can check for eavesdropping, and if none is detected, The key is guaranteed secure. The security comes not from the difficulty of a mathematical problem, which future computers might solve, but from the laws of quantum mechanics, which cannot be circumvented by any technology. China launched the Mikias satellite in August 2016 to test quantum communication over long distances using entangled photons. In 2017, the team demonstrated quantum key distribution between two ground stations separated by over 1,200 kilometers, a distance impossible to bridge with fiber optic quantum links due to photon loss. In 2020, they extended this to a satellite-mediated ground-to-ground link covering over 4,700 kilometers. A quantum internet, where photons carry entangled quantum states across global distances, enabling communications physically secure against any eavesdropping, is not a distant dream. It is an active engineering program. Photons also carry a property called polarization, which determines the orientation of their oscillating electromagnetic field. A photon's polarization can be horizontal, vertical, diagonal, or circular. It's a continuous property, meaning a photon can be polarized at any angle between 0 and 180 degrees. In classical physics, measuring the polarization of a photon simply reveals what it already was. You check the polarization. You read the answer. You move on. In quantum mechanics, a photon does not have a definite polarization in every basis before it's measured. A photon polarized at 45 degrees does not have a definite horizontal or vertical polarization. If you measure it in the horizontal-vertical basis, it has a 50% chance of registering as horizontal and a 50% chance as vertical. The measurement doesn't reveal a pre-existing value. It creates one. This is the feature that makes photons useful for quantum cryptography. A polarized photon carries one bit of quantum information, called a qubit. Unlike a classical bit, which is always either 0 or 1, a qubit can exist in a superposition of both states simultaneously. This isn't just a technical curiosity. It's the foundation of quantum computing, quantum cryptography, and the proposed quantum internet. In quantum computing, qubits can represent and process exponentially more information simultaneously than classical bits. For certain categories of problems, including the factoring of large numbers and the simulation of quantum systems, quantum computers offer fundamental advantages over classical machines. For the simulation of quantum systems specifically, the advantage isn't just speed. A classical computer trying to simulate a system of 100 entangled particles would need to track 2 to the power of 100 possible states simultaneously. That number has about 30 zeros. It exceeds the number of atoms in the observable universe. A quantum computer with 100 qubits can represent and manipulate all those states natively. Photons are one of the most promising candidates for carrying quantum information inside future quantum computers and between them. They interact weakly with their environment, which means their quantum states are relatively stable. They travel at the speed of light, and quantum operations can be performed on them using simple optical elements like beam splitters and wave plates. The same particle that carries starlight carries the quantum information that may define the next generation of computing and secure communication. The same particle that fills your room with light, that makes the sun visible, that carries the history of the universe in its frequencies, is also the tool humanity is using to build secure communications that no adversary can break without detection. Step back and take in the full picture. A photon has no mass, no size, no rest frame, no experience of time. It's a quantum excitation of the electromagnetic field, the smallest possible unit of electromagnetic energy. It carries energy proportional to its frequency. It carries momentum equal to its energy divided by the speed of light. It can behave as a wave, producing interference patterns and diffracting around edges. It can behave as a particle, landing at a specific point on a detector and transferring a discrete chunk of energy. It can be entangled with another photon across any distance. Its polarization can carry quantum information. Its exchange between charged particles mediates the electromagnetic force. Its vacuum fluctuations create the Casimir pressure between nearby surfaces. It can push spacecraft across the solar system. It can cool atoms to temperatures within a millionth of a degree of absolute zero. It can carry cryptographic keys with physical security guarantees. And it carries messages encoded in its frequency and direction from every corner of the observable universe, giving us our only direct view of cosmic history. And it cannot, under any circumstances, ever stop. Because to stop, it would need a rest frame. To have a rest frame, it would need mass. To have mass, it would need to be something fundamentally different from what it is. And what it is, at bottom, is one of the irreducible building blocks of physical reality. Not a thing made of other things. A thing that other things are made of. Every chemical bond holding every molecule together. Every electrical signal in every nervous system. Every star shining in every galaxy. Every bit of information ever transmitted over fiber optic cable. Every medical X-ray. Every GPS signal. Every broadcast. All of it comes down to photons. Real photons carrying energy across space. Virtual photons flickering in and out of existence, carrying forces between charges. Ancient photons that have been traveling since the first light of the universe. Fresh photons born in the collisions of electrons and positrons in particle accelerators. The question of what a photon is made of has a clean answer. It's not made of anything. It is the answer. The irreducible minimum of electromagnetic reality. And the question of why it never stands still has an equally clean answer. Because motion is not something a photon does. It's what a photon is. A photon at rest is a contradiction. A slow photon is impossible. A photon taking its time is something the universe simply does not permit. From the moment of its creation to the moment it's absorbed, a photon moves at exactly 300,000 kilometers per second in every reference frame, for every observer, toward whatever is waiting for it at the end of its journey. The night sky above you right now contains photons that left their sources 1 billion years before the Earth existed. They've crossed distances that strain every human attempt at description. They've been stretched by the expansion of space. They've navigated the vast, nearly empty cosmos, and they end their journeys, finally, on the surface of your eye. Not poetically, literally. Every time you look up, good night. The next time light finds your eye, you'll know what arrived. Something with no mass, no size, no age, and no interest in slowing down. A quantum ripple in the fabric of the universe, carrying the whole history of everywhere it's been, ending its journey exactly where it was always going to end. Right where you're looking.